Hello everyone, and welcome to another Aldic Riviera-PRO video. My name is Chantel, and this video will be about the image window/viewer. This is a tool that can be used to display an image stored in a memory-like simulation object, or visualize simulation object values by a color via a color map. It's useful for DSP or image processing designs, since the visual results can clearly and quickly verify that the HDL-based implementations work properly. And with these examples, I'll be able to highlight this usefulness. So, let's get started. For this video, I have Riviera-PRO's Modes example design opened up. This can be found in the Examples folder by going to Tools and then expanding the Image folder. This example contains 3 example Verilog designs, along with 3 macros to match them. These will highlight 3 different ways to utilize the image window. But before I jump into the examples, I'll show how to add an image. Head over to View in the main bar, hover over Debug, and then click on Image. The image window will pop up, and from there, click on the Add Image button. From here, an image can be added by using either a simulation object or a file. If object was chosen, make sure that the simulation has been initialized. If file was chosen, a number of options become available where more parameters can be specified. The file option also allows for the type selection of either an image or a color map. After selecting what image to add and its specifications, click OK to finish. When an image gets added and the simulation is running, the Synchronize option can be used to sync the image object with the current simulation time. Now we'll move on to the first example. This is the RGB example. In the Verilog code, RGB values are read from 3 hex files, and then their values are stored in the image RGB register. This is an example of what could be an image processing system performing image compression. In the project runme RGB macro file, the Verilog file gets initialized, and then the simulation runs at 10 nanosecond intervals. The IV commands, IV meaning image viewer, followed by add, adds a new image to the image window. The IV commands followed by image sets up the image parameters, including its name. The subsequent blocks of commands repeat this process at the 20 and 30 nanosecond time intervals. Now I'll go ahead and run the macro. And here are the results of the simulation in the image window. 3 images of a cat are produced, with all 3 results coming from the same image RGB object at different time intervals. At the 10 nanosecond mark, it can be seen that only the blue hex values have been loaded into image RGB. Then at 20 nanoseconds, the green hex values are added. And finally, at 30 nanoseconds, the full image has been produced with the red hex values loaded in. To the right of the image window, there's an image toolbox that can be opened by clicking on this image toolbox icon. In the Images section, hovering over one of the images displays its type and its source. Images can also be hidden or locked. And by right-clicking on the image or by highlighting and selecting this button, the image's properties can be edited here, such as its geometry, data, blending, and limits. The History option allows for highlighting differences in an image each time the image is synchronized with the current simulation time. Click on Apply and then OK if any changes were made. Now, without the image window, the other way of typically viewing the simulation results would be by looking at the image memory contents in a tabular alphanumeric format, which isn't always the most human-friendly way of looking at data. I'll end the simulation, close all the windows, and now I'll move to the color map example. In the color map's Verilog code, a hex file is read for a grayscale image and is then converted into floating point format and stored in the image grayscale FP real register. This represents an example of a DSP system that processes collected data and presents it as a color map image. In the color map macro, the color map file is initialized and ran, and the IV commands add two images into the image window. One image is the default color map, and the other is a color map with artifacts visualized. This IV command seen here is used to set custom color map table and interpolation settings. Now I'll execute macro. And here are the results of the simulation. As expected, two images are loaded, one with the original grayscale, and the other with the artifacts visualized. When hovering over either image in the Images section, it's confirmed that these are of the color map type. Earlier I didn't mention this, but by hovering over the images, the Details section of the Image Toolbox window updates with the details of the location of my cursor relative to the image and the window, as well as the different values produced from the image source at my cursor location. Again, without the image viewer, the only other immediate option to view these simulation results would be through a tabular alphanumeric view of the values. Also, that format does not have the ability to present the values in different color maps, which are useful for potentially denoting qualities like temperature on a thermographic map. Now I'll end the simulation and close these windows once again. And now I'll demonstrate the final example. This example uses the same gray hex file, but this time a measure mask is created to produce a transparent layer that will display over the main image. This example design demonstrates what can be a medical imaging device that can highlight a certain part of a scan. This also demonstrates the ARGB image format, where an additional alpha channel byte is added to the regular RGB byte set to enable pixel transparency specification. In the ARGB macro, ARGB is initialized and runs till 40 nanoseconds in simulation time. The IV commands are used to add the main image and the measure mask. And it can be seen that the IV command also sets the color format and byte order of the mask to ARGB. Now I'll execute the macro. And here's the result of our simulation. The image can be seen with the standard grayscale color map image, as well as the transparent layer of the measure mask used to target a certain part of the image. In the Images section of the toolbox, going to Measure Masks Properties, it can be confirmed that the data of the mask was set to ARGB, giving it that transparent appearance. Now by hovering over an area of the image and right-clicking, there's an Add option that allows for adding a pin, comment, or info box and placing it on the image. When adding any of the three options, they will also be added to this Widgets section. In the Widgets section, widgets can be hidden or have their properties changed. By hovering over any widget object in this section, the Details section updates to the information for that particular widget. Pins mark one particular spot on the image. Comments allow for making remarks on an area of the image. And info boxes mark the area, as well as add all the area's details onto the image. This allows for looking at the details without having to hover over that one particular spot. With the versatility of the image window and the utility of Image Toolbox, it's easy to see how effective this debugging tool can be, especially for projects revolving around DSP or image processing. Instead of looking at alphanumeric values, a visual can be used to clearly show the results of simulation, potentially reducing the debugging and verification time used during the design process. That is all I have for this video, and thanks for watching.